Welcome to the concept video for thermochemistry. I hope, as we requested last week, that you have read or watched your thermochemistry videos for this week, because it's going to keep you from being confused during this, or at least help you to not be too confused. There are going to be two sections to today's lab. The first one is exploring Hess's law. Hess's law simply states that the enthalpy change for a reaction is equal to the sum of the enthalpy changes for its individual steps. Now, delta H is a state function, which means it doesn't matter how you get there. What matters is where you start and where you finish, that actual change in enthalpy. So it doesn't matter how many steps you have to use, how few steps you have to use, or even which steps you have to use to get from reactants to products for a particular equation. The delta H for that reaction is going to be the same. So in part one, we're going to perform 3 experiments. One of them is going to be our target equation. If you look back at your videos, you'll notice that I tend to use 2 or 3 equations that we manipulate to get a target equation. So one we're going to be doing is actually our target equation. The other 2 are going to be steps that we'll have to manipulate to get to that target equation. The reactions we're going to be doing are, first of all, the dissolution of solid NaOH in water, which is simply NaOH solid becoming Na plus aqueous and OH minus aqueous. So this is a dissolution, and we're going to be measuring the delta H, and we'll talk about how in just a minute. The second experiment that we'll be doing is we'll be taking aqueous sodium hydroxide, so Na plus, I'm going to write this in terms of its ions, OH minus, so these guys have dissociated, H plus, and Cl minus. And this is a neutralization reaction, which means we're going to end up with liquid water, and Na plus, and Cl minus. And again, we're going to be finding the delta H for this reaction. Finally, we're going to be finding the delta H of our target reaction, which is taking solid NaOH and aqueous HCl. So here we go, starting with the solid NaOH, and we're reacting it with aqueous HCl. This again is an acid-base reaction. So again, we're going to get water, and we're going to get some ions. Same ions as before. And we're going to measure the delta H for this reaction as well. Now this is our target equation, so we're going to have to figure out how to use the other 2, reaction A and reaction B, which are our steps, to get to reaction C. But we'll figure that out in a minute. First of all, I want to know how we're going to figure out delta H, and so should you. We're going to be using coffee cup calorimetry, constant pressure calorimetry. Now remember, for constant pressure calorimetry, the delta H is equal to the heat given off or absorbed by that particular reaction. Check that out in your notes. That's important. This is constant pressure calorimetry, so we can figure out the heat, the change in enthalpy of a reaction, simply by measuring the heat released or absorbed. So now this is our coffee cup calorimetry. Now remember that in any kind of calorimetry, we have to obey the first law of thermodynamics, which means that effectively the Q system plus Q surroundings is equal to 0. In other words, the energy of the universe is constant. Q system plus Q surroundings is our Q universe. It's constant, so Q system plus Q surroundings is 0. Another way of looking at that then is Q system equals negative Q surroundings. Now the Q surroundings are the things we're going to be able to measure. And how is that? Well, Q system is actually, in this case, the Q reaction. System, remember, is the thing that you're studying, and what we're studying is the reaction. The way we can measure it is by observing what happens to the solution, which is the surroundings. So this is the surroundings. What's actually happening inside with the dissolution or the reaction is the system. Okay? So the surroundings is simply the resulting solution. All right, so what can we measure for the solution? Because obviously we have to measure something with that Q solution in order to figure out the Q reaction. And from that, we can find the delta H. So how are we going to measure this Q solution? Well, we're not going to be having any change in phase in these reactions. Everything's going to be aqueous. There's going to be no change in phase. So we're going to be dealing with a Q that we can find that is not latent heat, which means it's going to be using the specific heat. So our Q is going to be, for the solution, is going to be the mass of the solution times the specific heat of the solution times the temperature change of the solution. And this is very easy. Massing that solution's very easy. Mass the calorimeter cup, add the solution, mass it again. Very easy. C solution, well, what's that? Well, remember, this is a very dilute solution, and when a solution is very dilute, the C solution is equal to C water, which is 4.184 joules per gram degree C. And obviously, using the thermometer that's going to be in this cup, we can measure the temperature change. So given this data, we're going to end up with the Q solution. And the Q reaction is going to be equal to the negative of the Q solution. In order to find the delta H in kilojoules per mole, we're going to have to determine how many moles we've just used in the reaction. For the first trial, we're going to know the grams of the NaOH. How do you convert grams of NaOH to moles of NaOH? I'll leave that to you to figure out. For the second reaction, we're not going to have grams of NaOH. We're going to have milliliters of a sodium hydroxide solution that has a known molarity. A known molarity. So how are we going to figure out how many moles of sodium hydroxide here? I'll leave that to you to figure out. For the third reaction, we're back to grams of sodium hydroxide again. So however you did it for reaction 1, you're going to do for reaction 2. Once we have determined how many moles of NaOH we used for each of these reactions, we can find the delta H in kilojoules per mole simply by taking the Q reaction and dividing it by this number of moles. Okay, the Q is the delta H anyway, but we want the delta H in kilojoules per mole. So Q reaction divided by this number of moles will give you delta H for the second reaction, and Q reaction for the third reaction divided by this number of moles will give you the delta H. Okay, so that's fine. We now have done the reactions, figured out the delta H per mole in kilojoules per mole for each of those three equations. So now we have to figure out how we're going to manipulate these equations to get to the target. So again, we have NaOH solid dissociating into Na plus aqueous plus OH minus aqueous, and we will know the delta H per mole. So we're going to call that delta H per mole for 1. Number 2 is Na plus aqueous, OH minus aqueous. Remember, this is your two aqueous solutions, H plus aqueous and Cl minus aqueous will become or yields water, again neutralization reaction, plus Na plus aqueous plus Cl minus aqueous. And the target equation, this will have a delta H too. The target equation, whoa, that was bad, is going to be our third reaction. NaOH solid becomes water plus HCl aqueous. Let's do that again. Our target equation is NaOH solid plus hydrochloric acid aqueous yields water and Na plus and Cl minus. And we want to make sure that our delta H3 is going to be equal to whatever we have to do to delta H1 and 2. Okay, so let's figure out how we're going to do this. Well, as always with our Hess's law examples, you take a look at your target equation and you find where you're going to, which equations you're going to be using that has that particular compound in it. So first we're looking at NaOH solid, and the equation that we see that in, the reaction, is number 1. We check it out, it's got the right coefficient, it's on the correct side, so we're going to leave that equation alone. All right, so now we're looking for H2O liquid. Oh, here it is in equation 2. And it's got the correct coefficient, and it's on the correct side, so that one's fine too. We leave that equation alone. So now let's see if everything else cancels, because it looks like we've got a lot of extra stuff. Remember, we consider all the reactants on the left-hand side of the arrow and all the products on the right-hand side of the arrow, and we see if we can cancel anything out. Now let's see. I can cancel out 1 sodium on the reactant side and 1 sodium on the product side. I can cancel out a hydroxide on the reactant side and a hydroxide on the product side. Now, can I cancel anything else out? Well, sure I can. I could cancel out the chlorines, but given that I want them in my target equation, I'm not going to bother. So now that I've canceled things out, I've got NaOH solid plus H plus Cl minus yields water plus Na plus Cl minus. So it looks like all I have to do is add these two changes in enthalpy together to get the change in enthalpy for the target reaction. That was easy. We didn't have to do too much. Just had to add the two enthalpies of reaction together. If you were careful when you did this, your steps, the enthalpies of your steps, should be very similar to the enthalpy of the target equation. All right, so the second part is the heat of combination. We're going to be doing two experiments that involve a particular metal. You're either going to choose magnesium or calcium, and we're going to be finding the delta H per mole for each of the reactions. And the reactions we're going to be looking at, I'm going to use strontium because both magnesium and calcium are alkaline earth metals, so strontium, so I'm going to pretend that I'm using strontium. It'll react the same way as magnesium or calcium. So the first thing we're going to do is take the metal, the pure metal, and we're going to react it with hydrochloric acid. You're going to have to make sure you're using the correct concentration. This reaction is a displacement reaction, just like we did way back in the chemical reactions lab, and it will yield strontium chloride and hydrogen gas. Oh yay, that stuff that makes you choke. Doing the coffee cup calorimetry exactly the way we did before, we're going to be able to find the delta H in kilojoules per mole. We're also going to take the metal oxide, which again is a solid, and we're going to add some hydrochloric acid to it, and we're going to measure the temperature and the mass and all of that, and we're going to find, excuse me, the delta H for the reaction in which strontium oxide plus 2 hydrochloric acids yields strontium chloride and water, and we'll find the delta H for that as well. Again, we're going to use constant pressure calorimetry, so we'll be able to find the Q's for the reaction. We'll be finding the Q solution using MC delta T. Again, the C is the same as it is for water because this is a very dilute solution. And then Q reaction is going to be equal to negative Q solution, just like before. Once we find the delta H's, we can manipulate the equations, and including the equation for the formation of liquid water from hydrogen and oxygen, we can find the delta H for a combination reaction. So let's see what we need to do here. Okay, reaction number 1. Strontium plus 2 hydrochloric acids, aqueous yields, again, strontium chloride. This again is a displacement reaction plus hydrogen gas. And that will be our delta H1 that we will measure. The second reaction, we take the strontium oxide. Again, you will be using magnesium and magnesium oxide or calcium and calcium oxide. I'm just giving you an example using strontium. And that will be delta H2. The one that we're not going to let you do, but that you're also going to need, is the formation of water from hydrogen and oxygen gas. So hydrogen gas plus oxygen gas, remember with thermochemical equations we can use fractions, yields liquid water. And the delta H for that we're going to give you 285.8 kilojoules per mole. Now, the target equation for this that we want to get is strontium, in my case, plus a half oxygen becomes strontium oxide. And we want the delta H for that. Okay? So how am I going to manipulate these equations to get the target? Well, again, I look for the step equation that has the reactants and the products for the target equation. So which of the steps has strontium as an element and a solid? Right, step 1. And it's on the correct side and it's, or reaction 1. Correct side, correct coefficient, so we're leaving it alone. That delta H will be used as it is. Now, the second one, a half oxygen. Well, a half oxygen we find in step 3. So, or reaction 3. It's on the correct side. It's got the correct coefficients, so we leave it alone. And we're going to use that delta H as it is. Our final part of the target equation that we're looking for is strontium oxide. And it is in equation 2, but it's on the wrong side. So we need to reverse this equation, which is the same thing as multiplying the whole thing by -1. And when we multiply the whole thing by -1, we're going to end up, like I said, reversing the equation. And what's going to happen to that delta H? Yeah, the delta H, the new delta H, we're going to have is negative the original delta H. So I'm going to actually just kind of cross this whole thing off because I don't need it anymore. Okay, that's, whoops, getting carried away there. That's gone. Now I'm going to go ahead and add these up. So again, keeping all my reactants on the reactant side, all my products on the product side, and I'm going to see if I can cancel anything out. So let's see. What I want to end up with is the strontium, the oxygen, and the strontium oxide. That's all I want to end up with. So let's see. 2HCl. I need to get rid of 2HCl. Oh, here it is on the product side, reactant side. That's gone. Let's see. I want to get rid of strontium chloride. Oh, here it is. Strontium chloride on the reactant side cancels with strontium chloride on the product side. What else do I have? Hydrogen gas. I need to get rid of 1 mole of hydrogen. Oh, right down here in equation 3. On opposite sides of the equation, they cancel out. Let's see. Okay, so that took care of this. Going down here. Oh, I still have water that I need to get rid of in the second equation and in the third equation. So my water from the reactant side in the second equation cancels with the water from the product side in the third equation, and I am left with strontium plus a half oxygen becomes strontium oxide. So now I can add together delta H1 plus a negative delta H2 plus delta H3, and that will give me my overall enthalpy for the target equation. Okay, in the end of your calculation section in your lab document, there are actual values for the combination enthalpies for both magnesium and oxygen and calcium and oxygen. So again, you're going to be calculating the percent error. Try to be careful this week. Try to do the follow Mr. Proetta's procedure really closely, and you'll get really good values. If you get stuck, I'm going to be doing a sample set in processing the data video this week, and we can figure it out together. Okay, be safe.